Our project was the classic video game Tank City. The premise of the game is that the user is a tank trying to kill all the enemy tanks before they destroy the flag. The game ends if the enemy shoots the flag or the user runs out of lives. The game continues to the next level if all of the enemy tanks are destroyed. The game screen is divided into two sections, the gameplay area and the game info. The game info is the level, tanks to kill, score, and user lives. The gameplay area shows all of the tanks and the bullets and the blocks that are active in the current game. The primary actions of the game are the interactions between all of the moving objects. The following are the primary actions for the game. First, the user shoots an enemy tank. Whenever an enemy tank is shot, the tanks to go count is decremented, the score is incremented, and the tank is removed from the screen and respawned elsewhere if there are that many more tanks to go. Second, the enemy shoots a user tank. Whenever a user tank is shot, that user's lives are decremented, and the user is removed from the screen and respawned elsewhere if the lives are. Third, any tank shoots a block. Whenever a block is shot, the block is removed from the screen. Fourth, the enemy shoots the flag. Whenever the flag is shot, the game ends and the screen freezes with the game over screen.
Shoot the duck frogs down here. You're that good, I guess. Like when the duck is in the grass, you start shooting.
The biggest difficulty for the project is handling the large number of independently operating objects at the same time. Our game has 4 enemy tanks, 2 user tanks, and up to 6 bullets independently moving around the screen at the same time. This difficulty led us to implement an arbiter that would handle all of the action requests in a serial manner. However, even processing the requests serially led to many difficult corner cases. For example, a bullet can hit a block, a tank, or another bullet. If the bullet hits a tank, then that tank's pending request is no longer valid, and that tank has to be told so. Another related difficulty stems from the design choices that we made early on. We originally chose a 2x2 tile tank, a 2x1 tile bullet, and a 1x1 tile block. The 2x1 tile bullet causes the most issues because now a bullet can hit multiple objects from multiple orientations. For example, a bullet can hit any combination of 1 or 2 tanks, blocks, or other bullets from various orientations. These various orientations and corner cases make the state machines of the game very complicated and hard to debug, because now, instead of just having to compare a single point of an object, you have to look for multiple points of an object. A third difficulty comes with keeping the user interface in sync with the game state machine. The easier parts of this is the tanks to go, score, level, and user lives, because this information can be directly gotten from registers in the game state machine. The harder parts of this is syncing all of the tanks and bullet positions and orientations over time. Our solution to this was in the division of labor of the modules. For example, the AI and user modules hold a position and direction information and speaks a move information to the game state machine. The game state machine holds the game info and translates the move command info into an action info for the tiler to consume. The tiler will then translate the actions into multiple individual tiles. Finally, the VGA module converts the tiles into individual pixels that can be consumed by the monitor. This division of labor enables each piece to do small amounts of work and that are easier to debug and easier to build by themselves. The one place where we let too much happen is in the game state machine. This part of our design is very complicated because of 2 reasons. First, it has to communicate with many other modules. It talks to 2 RAMs, 2 ROMs, the arbiter, and the tiler. It has to convert move commands from the arbiter and AI user into actions that the tiler can consume. Secondly, it has a high computational effort. It does all of the checking for the valid moves and collisions for every object in the game. Even though all of the individual tile drawing information is not known to the game state machine, it's still very large and complicated. The solution to this problem would have been to break this one large singular state machine up into several smaller state machines that work together. However, this was not done due to the time constraints of the project. As far as testing the design is concerned, there were several small test benches built for the AI, game FSM, and tiler/VGA. However, it was difficult to debug these modules in simulation for 2 reasons. First, the design action times of the AI movement and the VGA display were very slow, so many clock cycles of time had to be run to get any meaningful data shown in simulation. The second, the outputs of the blocks were hard to interpret on their own. For example, the VGA outputs RGB signals for each pixel, which is hard to determine if you're actually displaying what you think you are. Since the tiler and VGA blocks were working very early on, most of the debugging for the game FSM and the AI were done on the FPGA itself. There is debug information that is displayed from the tiler and VGA in the lower right-hand corner of the screen. It shows the action, type, row, and column sent to the tiler from the game FSM. This enables the game FSM to be debugged from the VGA side.